Hello again everyone, welcome back to ptet.chemistry channel. So we're getting towards the end of this infographic video series that is kind of like an overview of how the A-level chemistry topics are linked together within the Cambridge International A-level. However, the way these topics are linked, it really is irrespective of whatever curriculum you're doing, because that's how the topics are linked together. This is the 9th out of the 10th video series on this infographic that are provided by Cambridge International Education for free on their Resource Plus website during the worst of the pandemic period back in March or April. So a copy of this infographic can be obtained on the Google Drive link in the video description below. First off, if you are looking for a video tutorial on your A-level chemistry topics, this video is not for you. If you are here to understand why are you learning certain stuff before other things, or why is the stuff that you are learning now, for example, if you're in year 12, why is that important for when you go to year 13 and stuff, alright? So in terms of organic chemistry, you would have known that formulaic representation, knowing how to draw display, structural and skeletal formula, being able to interconvert between the form at ease is very, very important to your success as an organic chemist, alright? Even your success as a student studying organic chemistry. So a lot of these are just dealing with different functional groups, such as a benzene, halogenoarine. A benzene is also known as an arene. Aromatic system means they have benzene ring. This is a OH bonded to a benzene ring. That is called a phenol. If this is NH2 instead of OH, that is called phenylamine. This is an acyl chloride. It's an extension of carboxylic acid, which are much simpler, and it's basically a more reactive version of carboxylic acid. This is amino acid. This is the simplest kind of amino acid where the R group is just H. This is glycine. It is one of many amino acids that are the basic building blocks of your proteins, okay, that make up our body. And this is the only amino acid that is not optically active, because it's got two groups that are the same, whereas when R is not hydrogen, you can expect the carbon there to be chiral due to the NH2 and CO2H, and the H, you have 4 different groups or substituents attached to the carbon. Therefore, you will have an optically active amino acid. Okay, so let's talk about arene chemistry. This is electrophilic substitution. Okay, not addition, because this is benzene chemistry. It will go via this intermediate. Is a carbocation intermediate where you break the aromaticity, so it's no longer delocalized completely, but then it really wants to go back to being aromatic. It will kick out the H plus, okay, and therefore you have replaced the H there with the electrophile. Could be bromine, could be chlorine, could be a R group, could be a acyl group, meaning R C double bond O, could be a nitro group, etc, etc. Those are all in a case study. You can watch my A-level topical playlist. I think it is in Introductory Organic Chemistry 10.1, but inside there's a video. There's a series of video that comes under the playlist A-level Organic Mechanism. It's got every single A-level organic mechanism that you will have to master, especially for your A-level synoptic paper, or equivalent to paper 4 for the Cambridge International. They can ask you anything from AS up until A2. The use of KMnO4, it can oxidize any side chain of a R group, okay, and basically a carbon bonded to an arene ring. You must have an acid for the KMnO4 minus to be able to do this side chain oxidation, and you will get this thing called benzoic acid. Alright, doesn't matter how long your chain is, it's just going to oxidize it, retaining the aromaticity and forming CO2H. This is H2. You don't do electrophilic substitution with a H2 molecule. Instead, what you do is you do reduction, because you really don't want to lose the aromaticity. What happens is you will need very high pressure and temperature, and of course you also need a catalyst. Otherwise, the reaction will be extremely slow for you to go all the way to this thing. I've just drawn the structural formula, which is also incidentally the skeletal formula, because the structural formula for a cyclic product, cyclic alkane, is the same as the skeletal formula. So 6 carbon, each carbon now becomes CH2, each carbon is now carbon sp3, each carbon is now bonded to 4 different groups, each carbon is now tetrahedral 109 degree, whereas previously it was 120 degree, carbon sp2, trigonal planar throughout. Okay. In terms of phenol chemistry, so there is a topical playlist under acid and bases. These are the kind of fixed acid. They always come out in A2 paper 4, where you're asked to compare acidity of phenol, normal alcohol versus carboxylic acid or versus water. The other one that is quite common, I'm looking for it here, is amine chemistry. They ask you to talk about basicity. So that essay is also in the acid and base section, in the acid and base topical playlist, as well as under phenol amine kind of chemistry. So they are dispersed all over the different playlists. If you go through it topic by topic, I'm sure you can find out where they are. So to get to diazonium, that is quite a key component. So one of the key reaction is you start from benzene, you form nitro, you reduce the nitro, and you form amine, and then you can go from there to there by using HONO, or what some books will write HNO2. You need dilute HCl, and you need to keep that cold, because if it is not cold, this N2 really likes to escape as a gas, and you will lose the N2 as a result. Okay, so you need to keep it cold at 0 to 5 degree. Because you use HCl, that's why you get a counter anion there. Okay, if you use a H2SO4, you will get SO4 2 minus with 2 of it, but typically we use HCl really. And then they are used to make Azo Dyes, where you react that with a phenol component. But of course, phenol on its own is not very good even though it's activated on the position 2, 4, and 6, depending on which one is available. It's still not very good in terms of activating it until you make it into O minus Na plus or O minus K plus. That becomes much better in terms of donating the electron density and activate the 2, 4, and 6 position. And to do that really you just use phenol with NaOH to get the sodium salt, or you use KOH and get the potassium salt, and then that reacting with diazonium, you would be able to get those things called the Azo Dyes. So I'm just gonna draw one for you here. So the O is gonna return to become OH eventually, because remember this is in acidic condition. Acidic conditions, these are in water, so the final step it can protonate again. Alright, so what happens is it usually doesn't like to go that way and that way because it's too close to the OH. So the one which is in terms of steric is the base is going to be this, where it's position 4, but it really depends if you're given the final product or not. Alright, that is the diazonium bit from the diazonium substance earlier. Okay, usually in a question they can ask you to write a balance equation between this and this to form this, so you should know how to write the balance equation, knowing the other byproduct as well. Okay, comparing the basicity of primary amine, which is like methylamine or any alkyl amine, versus ammonia versus phenylamine is a very common essay question, as I mentioned earlier. Alright, I'm going to move back up again, and we're going to talk briefly about carboxylic acid chemistry. The increasing acidity, basically comparing the acidity, was previously included here already. So you should know that phenol can react with diazonium, as I mentioned, can react with sodium because it's got a hydroxyl group. It can react with base, but it is not strong enough to react with sodium carbonate or potassium carbonate. So normal acid will react with these two to give you salt, carbon dioxide, and water, but not phenol, because even though it can react with NaOH or KOH, it can be neutralized. It's acidic, but it's too weak to react with carbonate. Can react with sodium because it's got OH. Can react with diazonium to form the Azo Dyes, as I talked about earlier. It can nitrate and brominate to give you white PBT, and it will activate position 2, 4, and 6. Okay, and it will go at room temperature, no need heating, and you can use aqueous or dilute condition. Basically, you use dilute HNO3, and you use bromine water, which is not even liquid bromine, so it's very dilute bromine in water. Okay, because this is highly activated on the 2, 4, and 6 position as given in your data booklet. All right, can relate it to alcohol chemistry, where you can take a alcohol and acyl chloride to give you an ester. So in terms of the ester bond that you're forming, this is the bond that you're forming. Esterification is the name of the reaction, but it's not the type. The type of the reaction, as you have known from your S, in fact O level, is called condensation, because you kick out a small molecule such as H2O, or you kick out a small molecule such as HCl. If you use an acyl chloride, you will kick out HCl. If you use a carboxylic acid, you kick out H2O. That's phenyl benzoate. So you can think about your starting material being acyl chloride and phenol. Okay, phenol and that will that's not going to be that great. What you can do is you can make this into a base, but this is reactive now, so this should react with this straight away at room temperature without the need for corn sulfuric acid catalyst, because you have a highly positive carbon there, highly delta plus carbon there, as a result of the two highly electron withdrawing groups there. Okay, that's basically the chemistry of acyl chloride. It can form ester, it can form amide, all right, as well. So you can hydrolyze that. So that is hydrolysis, and then giving you that and that. Both of them are what you call condensation. This is also condensation. This is also condensation to form the ester and the amides. Okay. When you talk about the amide chemistry, we talk about the C or NH bond, and that is the bond that we are breaking. When we do hydrolysis, we get back the carboxylic acid, if and only if we are under acidic hydrolysis. But don't forget that the amine that you get is basic. So when you do it under acidic condition, the amines will protonate, because what's the definition of a base? Whereas if you do it under base hydrolysis, what you will get is you will get the salt of the carboxylic acid. If I use sodium hydroxide, I'll get Na+. If I use potassium hydroxide, I'll get K+. But of course, then your amine is basic, and when you are in basic hydrolysis condition, your amine will not protonate, but your acid will get deprotonated. Okay, the reduction of amide, you see how the carbon there have lost the oxygen and gained the hydrogen. This is achieved by using LiAlH form, lithium aluminium hydride in dry ether. So lithium aluminum hydride is very sensitive to water, that's why we have to use dry ether there. Okay, as well as reflux. I talked briefly about amino acids earlier. That is not right. This thing is not right at all. Okay, so the one shown earlier was right, which was where is my amino acid? I forgot where is my amino acid already. There was a glycine just now. Anyway, I'll just draw it out. So that's not the right one for amino acids, because amino acid will have C and an R and an NH2, and then I'm just going to draw the three-dimensional structure like that. So I showed you glycine earlier, where R equal to H is the only amino acid which has which has no chiral carbon, because when there's H, they are the same. When R is anything but H, you're going to get a chiral carbon, a carbon bonded to 4 different groups or substituents. You're going to get optically active amino acid. Okay, this is, I don't know how to get it wrong, but this is essentially, there is an acidic group and there is a basic group, and then we can talk about things like Zwitter ionic interaction. Okay, the idea of applying power, then you can separate amino acid. This technique is called electrophoresis. There are certain factors that affect how far you move and how much you move, whether you move towards a negative terminal or positive terminal. These have been questions that have come up under electrophoresis. You can find the topical playlist under amino acids and proteins playlist for A-level chemistry topics to see how questions have been asked on that. All right. They then talk about homogeneous and heterogeneous catalysis. This can form part of an essay, especially the enzyme question, where you talk about active site, where you talk about enzyme, substrate complex, which is the intermediate, and then you talk about the enzyme is unchanged at the end of the reaction. That's why it's acting as a catalyst, but you've broken up the product as a form of metabolism, for example, in your body. Okay. The NO2, oxide nitrogen, and SO2, these are part of environmental chemistry. You should really know about the acid rain equations, how these form acid rain, how this one form acid rain. They are all in the AS level chemistry. They are in the nitrogen and sulfur playlist, topical playlist, under environmental chemistry. You will see that questions have been asked in the past, and a lot of students will struggle with the balancing question because they don't know what is going on, apart from acid rain, acid rain, acid rain. But you need to understand the chemical equation within and the redox reaction involved. These homogeneous and heterogeneous catalysis. So those are homogeneous catalysis. This is heterogeneous catalysis. These are in different phase. Then the thing that goes in, dirty stuff goes in, cleaner stuff comes out. Each of these you need to write equations, and they all come under the environmental chemistry as part of nitrogen and sulfur topical playlist, which you can check it out. I don't know why they put this under the organic chemistry, but I guess you can think about organic compounds such as this. What am I going to draw? So that is ethane dioic acid. It's an AS level case study. They love to ask you questions on this because this is a carboxylic acid, but you can oxidize it with acidified KMnO4 and heat. You can oxidize it. It will give you CO2 and H2O. If you deprotonate that, you are going to get this thing, which can act as a ligand. That is a bidentate ligand. It is charged. It is called oxalate, or simply ox. Okay, sometimes they just abbreviate it as ox. It's different, of course, from this thing where it's got a CH2 backbone that has got lone pair, and that is also bidentate ligand. That is called the EN ligand. It's ethylene diamine. They are bidentate ligand because one molecule of the ligand forms two dative covalent bonds to the transition metal center. And that's what your DNA does here. It's got these nitrogenous bases, and the idea of the nitrogenous bases affecting your copying of DNA data. People who do biology, you know about transcription, okay? And there's copying of your DNA data, and if your drug molecule, such as cisplatin, coordinates onto the nitrogenous bases, you prevent them from copying and dividing. If you don't get the cancer cell dividing, you can stop the spread of cancer, and that's why cisplatin can be used as an anti-cancer drug. However, it's the cisplatin where this is 90 degrees to each other, not the transplatin, because the geometry will not be aligned. Okay, so there's transplatin. Your DNA cannot bend around to fit it like that, but your DNA can coordinate to this side of it, okay, like that. where this one can come off, and your DNA nitrogenous bases can do ligand substitution reaction and bind it to the platinum 2 center. This is isomerism transition metal complex. Check out the transition metal chemistry playlist and you will find out more examples of these kind of isomerism questions that have come up in the past and how I go about doing them. Okay. The last bit of this organic chemistry, I suppose, is on this type of condensation polymerization. So nylon and terylene are your case study from GCSE and O level. The big thing really is in A level, you're expected to know the structure, okay, and they'll give you compound and they expect you to identify what is condensation, what is the definition of condensation polymerization, okay. I talked earlier about the definition of a condensation reaction, which you have covered in your AS Introductory Organic Chemistry, and you also covered this in your O-level and GCSE. Relate them together, master your concept, watch the topical playlist, not just on the addition polymerization, which is an AS topical playlist, but also on condensation polymerization, which is a big topic in A2 chemistry. Okay, predicting the type of polymerization, whether you end up with addition polymerization, where you add a cross-alkene, or you end up with a polyester or polyamide. In this case, you get a polyamide, the CONH, they continue there. In this case, you get a polyester, all right? And then, of course, we need to think about the properties of the polymer, where they can take in the Teflon, which is an addition polymer, textile and clothing, that is your, terylene, okay? Use of terylene, super glue is adhesive, is in your A2 polymerization case study, okay? So you got to know what it is. And these things, DNA, so they involve it's a protein chain, so it's involved polyamide, but because they are natural molecule, so they have a specific name. They call them polypeptide, but polypeptide are basically proteins, and proteins are basically polyamides, but they call it peptide. A peptide bond is a CONH, which is also known as an amide bond. So CONH is what we call amide, but if they exist between amino acids, then you call them peptide, but they're essentially the same. All right, that is the Teflon used for making cooking pan. Strong CF bond, high in bond energy, doesn't break easily, therefore not toxic to you if you cook at a high temperature at all. Polymers, of course, we're dealing with properties. Things that are biodegradable can be hydrolyzed. Things that are not biodegradable cannot be hydrolyzed. When you burn them, it either gives you harmful combustion product like CO, or when you have a CCl bond, it can give you harmful toxic gases like HCl or HCN if you have a CN on the side chain, all right? Synthetic routes to organic compound. This is the kind of questions that involve every single little mechanisms and reactions, conditions, reactants, those kind of things you learn all the way from O level, AS, as well as A level chemistry. So this is the end goal really, being able to identify what you start from and what you want to end up with, and think about your strategy. Okay, it's one of the things that scares students the most, but it's one of the fun thing in doing A-level chemistry is by the end of it, you'll be able to have a variety of knowledge to help you access this different synthetic route to very useful drug molecule. This is the end of this infographic series, I guess, on organic chemistry 2. So I'll see you in the next video, which should be the last one of the 10 video series on this infographic from Cambridge. They are by no means an overview or summary of your specification or syllabus. For that, you have to refer to the actual document. And what I've done here really is to just show you the connection between the topics and outline where you can find in my A-level chemistry topical playlist, where you can find in the relevant stuff to what you need to know, to whatever is stated in your specification and syllabus. Okay? So thank you for watching, and don't forget to subscribe and share the channel with people you know, like friends, your class group chat, your relative, your teachers, whoever else you think might benefit from this video on my channel. Okay, thank you for watching again.